So today we are going to talk about two problems. The first is the following. What is the minimum number of hyperplanes in the Euclidean space that dissect all edges of the hypercube graph in n dimensions? So just to be on the same page, our hypercube graph has vertices 2 to the n vertices, all the 0, 1 strings of length n, and two vertices are connected if they differ only the single coordinate. A hyperplane is defined using a linear equation in real number, and we say that a hyperplane dissects an edge if the two ends of the edge are strictly on different sides of the hyperplane. So let us make a simple example. What happens at dimension 2? How many lines do we need in order to cut all 4 edges? So we may have this configuration, for example. However, which involves two hyperplanes, but we cannot have this configuration because it dissects the edges on vertices. Now, what happens in dimension 3? How many planes do we need in order to dissect all 12 edges? So once again, we can do this with n planes. We can have planes which are orthogonal to the axis, like the example n equals 2, and we can also have diagonals running through the cube. And it gives us this general bound. And actually, if you think about this problem a little bit, it is not clear at all that h of n may be any smaller than n. Now, there is an example of Michael Kapralov, several years after the problem was introduced. It shows that h of 6 is smaller than 5, and you can blow this example up to get this general bound. And there are also some known values for h of n for small n. And this is what we know for upper bounds on h. And well, nowadays your talk does not count if it does not mention machine learning, so we give an application to neural networks. Suppose you want to construct a circuit that is given as an input n bits, and you want to compute the parity of these bits, the sum modulo 2 of these bits. And in your circuit, what you are allowed to do is to use threshold circuits. That is, you sum several input bits with coefficient, and your gates compute whether this sum is larger than some threshold. This is a basic problem, and one application for knowing the value of h in this context is that we claim that the first layer of any circuit that computes the parity function has at least h of n gates. Why is that? Suppose you have less than h of n gates in the first layer of the circuit, then you can consider the f spaces that they define, and there are going to be, because the number of these gates is smaller than h of n, there are going to be two adjacent vertices in the hypercube for which the first layer of this network is going to be the same for these two vertices. Now, because they are adjacent vertices, they should have a different parity value. So this is a contradiction. In the end, we get different values. This is one application, and now I want to give some history of this problem. This problem was first introduced in the 70s, and O'Neill asked what is the value of h, and he gave the motivation we just discussed. And he also showed the lower bound of sqrt of m for this value. We will see in a moment this argument. And this problem was studied also in some restricted regimes. So, for example, Alon and Quarles showed that if the hyperplanes have coefficients which are only plus or minus 1, then you need n over 2 hyperplanes, which is this is a type lower bound. And the proof uses the polynomial method. Later, Alshud and Zan show that if all the coefficients of all the hyperplanes have the same sign, then we need at least n hyperplanes. This is again type. And they use another method using LIM type inequalities. This is looking at the concept of defining the hypercube and using some anti-chain inequalities. And only 50 years after the problem was introduced, Yehuda and Yehudayev gave a genuinely new bound on h. They show that h of n is at least n to the power which is slightly more than 1f. And one thing we will discuss today is the proof of a lower bound of n to the 2/3 for the same problem. And as you can see, all the methods for tackling this problem are quite diverse, and it relates to many problems. For example, the Banks lemma that Yehuda and Yehudayev used, it is some underlying idea behind the Hopfield network concept that just won the physics Nobel Prize lately. And another nice problem that, the original problem that Bang introduced his lemma to solve what is called the Tversky's trunk problem, which is the following. Suppose you are given a convex set, and you want to cover it using planks. That is, you want to cover it using pairs of hyperplanes which are parallel, and you want to cover this set using the minimal total sum of widths of these planks. So this problem was famous in the 30s and 40s, and the answer given by Bang is that the sum of widths should be at least the diameter of the convex set. Okay, so this is.
Bang was in dimension 2 or just?
It was in any dimension. Okay, so this was some history. Now I want to talk about another problem, a very related problem, which is covering the hypercube. So now we discussed intersecting all edges in the cube. Now we want to cover all the vertices of the cube using hyperplanes. So how many hyperplanes do we need in order to cover all vertices? Yeah, we only need two hyperplanes. We can have the hyperplane. You can see this? Okay, so you can have h1 equals to h1 equals 0, and h2 is x1 equals 1. So this is not a very interesting problem. However, I mean, in this example, we used only the variable x1. One way to make this problem make sense is to restrict the hyperplanes to have non-zero coefficients. Now, if all coefficients are non-zero, then linear and Radhakrishnan showed using the polynomial method that you need at least n over 2 hyperplanes. And actually, the exact value for the number of hyperplanes is not known, but this problem is mostly solved. But this problem, again, is not, I mean, it was somewhat easy to prove this result. So Lineal and Radhakrishnan gave a more subtle way to formulate the problem that it will make more sense. So they introduced the notion of essential covers. We will later formulate the exact this exact problem, but just for now, I want to give a scheme of the results in this area. So for this problem, they show the lower bound for the number of hyperplanes to be square root of n. Then in a sequence of works, it was improved until last year, Sauman and Xu showed that a lower bound of n to the 2/3. Now, I found it, when I saw this paper, I found it quite interesting that it gives the same n to the 2/3 lower bound. But really, I mean, it uses different methods than our proof. So it was interesting to me whether maybe we can combine both methods to get a better result. So what I'm going to do in the rest of the talk is to present I mean, heuristic ways to heuristic proof, heuristic versions of both proofs, and show that why I believe there should be a way to that these proofs are somewhat complementing each other, and I believe it is a good direction maybe to think how to combine them. Okay, let's start about slicing edges. So we want to show, first let's start showing that h of n is square root of n. This is the classical result that was known from the 70s. The proof is basically just saying that each hyperplane cannot dissect more than a fraction of 1 over square root of n of the edges. This is clear that you must use square root of n hyperplanes to dissect all the edges. The proof of this about this proportion of edges, this is just it is equivalent to that the influence of f spaces is bounded by square root of n, or even influence of monotonic Boolean functions is bounded by square root of n. This is exactly the same thing. Now I want to propose a reason for maybe why this problem was, I mean, there was no, we did not advance on this problem for 50 years. The reason for that is that if you use square root of n hyperplanes, you can dissect almost all hyperplanes, almost all edges. So if you want to claim that there exists, it is hard to claim that there exists some edge when almost all edges are in hyperplane. So I want to explain this. So let's look at the hypercube. So this is the hypercube. We have here the single vertex with Hamming weight 0, and in here we have the vertex with Hamming weight n, and in the middle we have all the vertices sorted by their Hamming weight. So yes, now if you use hyperplanes, which are the form sum of xi equals to n over 2 plus or minus small things, then this hyperplanes corresponds to lines looking like that. That cuts the middle of this drawing. Now, if you make the computation, you can see that if you use like O of square root of n hyperplanes, you cut almost all the edges because most edges are in the middle layers of the hypercube. So this is unfortunate. A random edge is going to be dissected using these hyperplanes. Because of this, Yehuda and Yudayov came up with a clever idea to overcome this difficulty. What they said is, well, if you count all edges that are dissected in the using some hyperplanes, you may end up with almost all the edges. But you can introduce some other distribution that is different from the counting measure that maybe will evade this set of hyperplanes, right? So here is a toy problem for you. Suppose you are given only hyperplanes which are diagonal. That is, they are defined using this kind of equation that the sum of x's is equal to some value. What kind of distribution is going to evade this type of hyperplanes? We want that each hyperplane will only dissect a small fraction of edges using this distribution.
Uniform on the levels and then uniform in each level?
Right. So if we just choose a uniform layer in this picture and a random edge in this random layer, we are likely to evade any kind of hyperplane because the hyperplane will dissect 1 out of n layers. So this is a good idea. Now I want to make this somewhat to dive a little bit further in this example, because this idea really gives a lower bound for the general case. I want to demonstrate this. So the idea we are going to use is this notion of layers. You can actually generalize to a broader context. That is, what we did is that we had this direction, which we had this direction V, which is the all ones vector, that it is associated with the Hamming weight, and we claimed that each hyperplane, which is of the restricted form we discussed, is going to be only a single point when we project it into this axis, which is parallel to V. So each hyperplane is going to be just a single point. Now, each edge is going to be, each edge in this picture is going to be some interval in this, using this projection. And the point is that the edge intersects the hyperplane only if the projection of the edge intersects the projection of the hyperplane. This means that the interval we got and the point we got, the interval contains the point only if the edge intersects the hyperplane. This is the main idea we are going to use. And let us just analyze the case we just discussed. So if we take a random vertex which has a random Hamming weight, a uniformly random Hamming weight, then the inner product of x and v is going to be a uniform number between 0 and n. Now an edge, a random edge going out of this vertex x is going to have the length of the projection of this edge on v is going to be 1. Now, because the hyperplane is just a single point in this range, we must use at least n points in order to capture all intervals that go in these n options. Okay, so this is, this is just a toy case where all the hyperplanes are parallel. Now let us go to the general case. Now we have m hyperplanes, and we normalize the normal vectors to have 2 norm equals to 1. What we are going to do in the proof is to give a distribution over vertices, and we are going to take a random edge that is incident to this random vertex. And now, what we want to show is that the interval that corresponds to the projection of the edge on any normal vector contains the point that is obtained from the hyperplane projected on its normal vector. We want to show that this probability is bounded by 1 over n. When we do this, we just use union bound to say that the probability that E crosses any hyperplane is at most, we go over all hyperplanes, and the probability to capture this hyperplane is at most 1 over m, and this is why we will finish once we give such a good distribution. So our input is this hyperplanes, and we want to give a good distribution that will satisfy this projection inequality. What we need from this distribution is 2 things. First, we want the interval to be short, and if our interval will be large, then we will likely capture the point. So we want it to be short. And furthermore, we want that we'll have a lot of variance for the location of the interval when you project it on the normal vector v. And if we manage to do this, we will just generalize the case we have seen before. Now, I just want to say that the first requirement is a non-issue, and what we are going to do in this talk is just to assume that all our normal vectors are just generic, in the sense that the L infinity norm of our normal vectors is about 1 over square root of n. this holds for generic vectors, and in this case, the projection of any edge on a normal vector is going to be one of the sqrt of n, which is the shortest possible, and it is also the generic case. So we only are left with showing the second property. Okay.
So I mean, when you restricted those v's, you sort of restricted the number of hyperplanes you can choose. So could you justify why you can do that?
Yes, I have a slide on this later. If we can go to the details, but I mean, really, it's not a loss to do that because these are most of the hyperplanes. Okay, so we want to have a distribution over vertices, for which if you project the vertex on any normal vector, you will get a high variance random variable. How do you do that?
What is this? Where do you get the square root? Because VLs are arbitrary, no?
Yeah, but I assume that they have L2 norm equal to 1. And if you just choose a random vector with L2 norm 1.
What? Are VLs random or are you doing a distribution?
No, they are not random, but just for the presentation, I'm going to assume this genericity assumption, but we'll see later how to remove it.
But there's probably some logs that are in the generic.
Yes, I just signed the entire document.
That's just 1 over root n, right? But you want 1 over n.
Right, so what we need to do is to show that the variance of the location of the vertex projected on the normal vector to be larger than 1. And it makes sense because the M cube is quite large, right?
Okay, but I saw the points on the because the points after this projection, which is hyperplane VL, is going to be separated with distance 1, is it?
Right. No, they're actually going to be. They'll be separated with this distance.
Okay.
And finally, we will have the length of the interval. In this case that we have before, we wanted that the standard deviation of the location of the interval to be much larger than n times larger than the length of the interval.
Okay.
So we will not manage to have this separation of factor of n, but we only hope for a factor of n. This is sufficient. Okay, we'll see this in a moment. Okay, great. So you want a random vertex with high variance of the value of x projected on V. And you only have a small set of vectors. So how do you do that? One basic thing is to take just a random combination of the vectors V. This will give you, this will have this shape of this distribution. The shape corresponding to this distribution will have high variance on each axis. So one technical issue is that we are going to choose a point in the solid cube, and later we are going to round it to a proper vertex. So just leave it alone for now. And again, the way we are going to choose this point P in the solid cube is to take a random combination of the vectors V, offset this to be inside the cube, and then scale it by a factor C. So we need two things about P. We need P to be inside the solid cube, and we want P to have as large variance as possible when you project it on V. Now, let us analyze how large, the largest C is, the larger the variance of P projected on any normal vector. Now, let us see how large we can have C. Okay, so our point P is inside the solid cube, so we want that if you consider any specific coordinate, it is going to be smaller than 1. So let us consider some arbitrary coordinate. So, so we compute the sum from j equals 1 to m, and we look on j times vj at coordinate k, and forget the constant term. We want this to be smaller than 1. Now, in the generic case, recall that we assume that these values are about 1 over square root of n. So we have here just sum of independent random variables. For the worst case, we can assume the coefficients are just 1 over square root of n. We have sum of m such random variables. And so we just need that using variance, any Chernoff bound or something like that, you can see that we only needed C times square root of m over n to be smaller than 1. So this means that C may be Si as square root of n over n. Okay, so this is upper bound for C. And now I want to analyze the variance of the point P projected on V.
Sorry, but here you don't only have that this is in 0, 1 with high probability or something, right? Why is that enough?
What is going to be?
So in the worst case, you have is if you have epsilon all ones or something. So you will have points where this is larger than 1.
Yeah, I aim for the average case where epsilons are going to be just random and with high probability.
So you just want P to be with high probability and whatever.
Yes. I just want to find. Everything is probabilistic. I only talk about measures of stuff.
Okay.
Right now, the next property we want is that the projection of P onto the normal vector V, we want to have high variance. So let us just compute this projection. So you just take inner product, and you get this expression. Now this is again just the sum of independent random variables because the epsilons are independent, and the variance of this random variable of P projected into V is larger than just the variance of C times epsilon L times the L. So in here I just substituted J equal to L and only took this term, just one term. So we can guess this inequality is quite lossy, but it will be enough. So what is the variance of this random variable? So the variance of this is constant. This is just equal 1. And so we get that the variance is c squared. And the standard deviation is going to be just exactly c. Okay, so let us just finish the argument. So we have an interval. We have an interval of length 1 over square root of n. Its location has standard deviation c. And I mean, how many points do we need to capture this interval having this large standard deviation? We get this exact expression, and this should be smaller than 1 over n, because this is what we aim for. Now let's just substitute everything. C equals square root of n divided by n. We have divided by square root of n divided by n. It should be smaller than 1 over n. Now you can play a little bit with that, and you need that yes, m to the 2/3 should be smaller than n. So this is why the proof works up to this point. Okay, just a few remarks about this proof. The way we round a point in the solid cube to a vertex is basic. We just take a random vertex with this bias of p. We take xi to be independently of the other coordinates, to be 1 with probability pi and 0 with probability 1 minus pi. I mean, x is going to behave like p, and yeah, the proof just works quite smoothly with that. And I'm going to skip it, but we can also avoid the issue that we assume that all the coordinates are small, but there is a simple way to avoid this assumption.
So yeah, is epsilon I from the previous slide?
V?
Ti is the epsilon I on the previous slide?
So P, yes, it was the linear combination of the vectors with coefficients epsilon. Yes. Now, the point I want to make is that the odd instances for our proof are sparse vectors V. Why is that? Because we had only one lossy inequality in here. That is, I mean, when we computed the variance of P projected onto V, we got this expression, and we just lower bounded the variance of this by substituting J equals L and just forgot everything else. And this is, generally, this is very lossy, and it is not lossy only for sparse vectors V. Okay, so let us just keep in mind that this proof was tight only for sparse vectors. Now I want to go to the second problem. How to cover the hypercube using hyperplanes. So recall that Lineal and Radhakrishnan started with wanting to cover the hypercube using hyperplanes. And this problem does not make much sense because you can have just two hyperplanes that cover everything. Okay, so we need to add something to this definition. So what they do is to requires that every coordinate has some non-zero coefficient in one of the hyperplanes. Well, does this formulation make sense? I mean, you can see that there is 3 there, so no. So if you just add H, which is just a dummy hyperplane, then I mean, the problem is still not interesting. Now, if you require that this configuration is minimal, that is, every hyperplane is not dummy, then this problem makes sense and it is interesting. And in summary, the problem is just written in above. And this configuration that satisfies all this requirement is called an essential cover, and they ask what is the minimal essential cover. So what we do next is to give an outline for the proof of Sauermann and Rousseau. The general idea of the proof is to give an algorithm. The input of this algorithm is a set of hyperplanes, and what they want to do is just to give a point that is outside of these hyperplanes, basic. The general method they are going to have, they have three steps. So in the first step, they found a set of good coordinates. So they arrange all normal vectors V in a matrix. As n normal vectors and n coordinates, and they found a set of good coordinates. That's the first step. The second step is to find a point in the solid cube which is far from all the hyperplanes that we are given. By the way, I call the Tarski-Planck problem, in which you claim that small set of planks, planks with low widths do not cover the convex set. Okay, so in the second step, they found a point in the solid cube which is far from all the hyperplanes. And in the last part, they just round P to a vertex. This is exactly the same rounding that we discussed before. Now, just what is this condition on the second step that you use in the third step? So, because we require that our point P is very far from all the hyperplanes, if you round the point P to a random vertex using our randomization technique, then the inner product between X and V is going to be the inner product between X and V is going to be close to the inner products of P and V, and the deviation is going to be about the L2 norm of V. So this exact requirement was used in the third step.
What's the normalization with the L2 norms here?
Pardon me?
So what's the normalization for they're not unit vectors anymore?
The normalization.
The VLs are not unit vectors?
So we'll assume it is normalized, but this will not formulate this in it. Okay, so let us start with the third point finished. Now let us talk about the second step, which I remind you is similar to the Tarski-Planck problem. So the idea they use in the proof is following. So they are going to choose P to be again just the sum of the vectors V times epsilon. So this is from J from 1 to M. And now they're going to take epsilons, which are plus or minus 1. I mean, they're not random, they're just in this set. Now, let us formalize, forget about Planck's lemma. Let us formalize what we need. We need that P times VL minus T to be large. So let us open this expression. So we have a sum of J from 1 to M of epsilon J times Vj times Vl. And we want this to be larger than 1. Okay, now you see here that we get all the inner product of two normal vectors, and and we just need this M requirement. For this, we use the same. I mean, recall that we use the same thing as the Tarski-Planck problem. So let us use Planck's lemma because this is exactly the same problem, right? So what Planck's lemma says is the following. Suppose you are given a matrix G, which is symmetric, and suppose you have some arbitrary numbers. Then we have some vector epsilon of plus or minus 1 with this requirement. It looks pretty similar to what we need. We need that we need this kind of expression. Now, if we just take G to contain all inner products of our vectors, so suppose this matrix is called B, and you take G to be B times B transpose, then we get that I mean the diagonal of G is going to be 1, and the inequality in Planck's lemma is just going to be what we need. Okay, so this was quite too easy. We forgot one thing. We forgot that we want our point P to be inside the solid cube. I mean, actually, this part of the proof could take care for M take care for larger M. So what really bounds us is that P needs to be in the solid cube. So what we want is that P is just going to be a sum of these rows, and in order to have all coordinates of P small, we need that the sum of each column in absolute value to be smaller than 1, smaller constant. This is more convenient. So we want the sum of each column to be small. Now let us have some sanity check. What is the, suppose we have some random, vectors in here. Let's say if we can satisfy the sum of each column to be small. We need the sum of each column to be small because we basically sum each column with coefficients, and in the worst case, we need the sum of absolute values to be small. So in the general case, our matrix B is going to have all entries being about 1 over square root of n. So everything is 1 over square root of n, and the height of the matrix is going to be n. Now, what is the sum of each column? So the sum of each column is going to be just m divided by square root of n. And this is not going to be smaller than 1 if we want a large n. This works up to n, which is of the order of square root of n. We want to go higher than that. Okay, so not good. And what Sorman and Xu do is to use result of linear adaptation. They showed that in the interesting case, if you have an essential cover, then the vectors are going to be sparse. You only have about m non-zero coordinates in each vector. Okay, so let us reanalyze our example. So in the worst case, you can think about it. In the worst case, each vector will contain about it will contain m non-zero values. Each of magnitude 1 over square root of n. And recall that we want the sum of a column. So what is the average sum of a column? So let us compute the sum of all columns. So this is just to compute the sum of all entries in here. So we have m vectors and m entries in each vector, which is of size 1 over square root of n. This is going to be in total m to the power 3 over 2. Now, in average column, we are going to have this divided by n. And this is an average column. Because we need each column to be smaller than 1, then we just need that m to be of the order of n to the 2/3. That's the idea. Now, actually, we need that all columns to be good. It's not sufficient that an average column is good. And for that, Sorman and Xu show how to remove coordinates. That is, there are bad coordinates which have I and L1 no. What they do is to this is just something specific about this problem where they take the so suppose we have a column with I L1 norm. So you get this to the bad columns section. And now, using that we are talking about essential covers, we are going to have some non-zero coefficients in the good part of coordinates. And because we are talking about an essential cover, this non-zero coefficient is used in some hyperplanes that is not dummy, and this means that there exists some substitution for these coordinates, which make this cover of the rest of the good columns, which keep it a cover, a non-trivial cover, and I mean, then you apply everything on this set of good columns. So this is really not very important. There is something specific about essential covers that allows you to remove bad coordinates. Now, the point I want to make is that in our worst case example, we had our matrix as dense as possible. So we had a restriction that every vector has at most this value of non-zero values, and the hardest case is when the vectors are most dense. And this is the point I wanted to make, that in this problem, hard instances are dense, and in the previous method we had, the hard instances are sparse. So I hope maybe we'll be able to combine these proofs. I think so. I just wanted to show that there is a very short proof of Banks' lemma to make the talk more self-contained, but I think we'll skip it. But there is a really short proof for Banks' lemma, so there is really no magic